17768. I get difference. So hold on, 2500 times 2 plus y72 123 divided by equal divided by 2 divided by shift pi divided by 2 power 3 squared 2346. Yep, I got the same. Okay, then the next term is equal to 55200 divided by pi and then times by c power of 3. Okay, then bracket the whole thing again, and then power of 2. Okay, so let me see. So 55200 squared, or 55200 divided by shift pi divided by 2 power of 3 squared squared 483.4823902. Okay, close enough. Okay, then you have the minus 50 power 3. Okay, so the final answer over here is equal to square root of this term plus by this term. They've been squared already, right? And then minus by 50 power 3. Okay, I wonder why my 50 power 3. Oh, okay, my bad. So minus 50 E3. There you go. Okay, so once you have done that, right, you just go here, you just go to forecast. Let me expand this view first. Okay, you go for what if. Okay, what if, you can see that. So I click go seek. Okay, so set cell is the cell that is calculating the final answer, which is the 52677.78. Okay, then the value, you want the value equal to 0, right? The whole value equal to 0, and then by changing the cell over here, okay, and just press OK. So the thing is thinking now. I think I make a mistake. So the computer is still going, but this is not the right answer, and my mistake is over here. This is just 50,000. I put it as minus, okay, which is wrong. So again, I start from 2. Okay, I start from 2. Again, what if, right? Go seek. Okay, so this number over here has to be equal to 0. Why it has to be equal to 0 is because if you look at function, this term over here is equal to what? 0, yes or no? Right? So that's the only reason. Okay, then by changing the C, and then you put OK, so the thing will go. So now if you look at your answer now, they say that the correct answer is 0.75. I did not do this. Okay, so let's say now I do this. Okay, I put 5. Okay, I say what if go seek. Okay, this the current minus 49,823 is equal to 0. By changing C, you just put OK. Okay, so that is your answer. So 0.750569. Now sometimes I'm not sure whether have you all done numerical methods. Okay, so sometimes the initial position is very important. So let's say if your initial position is 0.001, you don't know. Okay, you just put any. So now if you go to go seek, okay, now this is a limitation of using Excel. If you were to use MATLAB or Wolfram or CADRAM Alpha, whatever, it will work. Okay, but if you use Excel, okay, so we might not get a solution here. See, it's still thinking. Oh, you might. Oh, they've changed something about Excel. Or if I guess this to be very big, maybe if I guess this to be 5,000, see what happens. Go seek 0 by changing this cell. Let's see what happens. See, it can't do it. So the initial guess position is very important. See, it's not getting your answer, right? So if that's the case, 5,000 is too big, so you put 0.1 as your initial guess. You put what if, go seek, change to 0 by changing this cell over here. So this will be equal to, there you go. So it's 0.750557. Okay, so that is our answer. So because our exam is online, you can use, I mean, I'm just showing you Excel, okay? Not necessarily you have to use Excel. You can use anything, okay? There's no way I'm going to check. Okay, so this is our answer. Wait, hold on. Where is my mouse now? Right, so using solver in Excel or Microsoft Excel. You can use your calculator also, by the way, okay? Yeah. The C value is equal to 0.7506 inches. Okay. So I round it off. Okay, I round it off. So therefore, I think this question wants to ask radius or diameter. Let me see the question. Diameter. Okay, so diameter of the shaft is equal to 2C. So this is twice multiplied by 0.7506 is equal to 1.5012 inches. Okay, so that is the shaft that we're going to use. Okay, so that's the shaft we're going to use. So this is how we apply Tresca criteria. The thing to watch for, the most critical thing to watch for is this formula over here. So as you can see, when we started the lecture, there are several conditions. Yes, there are two conditions. Okay, so if okay, when one of the principal stress is equal to 0, then you can use this number over here. Okay, if not, you have to use this formula over here. Okay, when the principal stresses are positive, and this can be analyzed by just like what I've just done. Okay, by just sketching. Right down here, we don't know our value yet. We just sketch our 3D mole circle. I repeat again, this is 3D mole circle. We're not using 2D. Okay. Okay. So identifying the stress load is already it's not difficult, okay, but you have to be very, very cautious. Okay. But for this case, the example is pretty straightforward. It gives you the moment, it gives you the torque, it gives you your bending. Now, questions like this can be can be an example like this. Okay, remember we did this, right? We calculate the stress state, right? We calculate everything, right? So it can be examples, it can be problems like this. Okay, for example, it can be problems like this. Okay, this is the loading condition, right? So I will tell you that, okay, select. So for example, you don't know what to use down here. Okay, I can say that, okay, what if we are going to use material that has a yield stress of 600 megapascal using Tresca criteria. Just an example. Okay, so you can go either way. Okay, or select the material based on Tresca criteria. Okay, so it's all 3D mole circle stuff. Right. So the next criteria that we're going to do, so we've finished with Tresca. Okay. Now, by the way, this example I show you is one of the most, it's one example that shows you the procedure, the full procedure on how to design a shaft, now including axial load, okay, with Tresca criteria. Okay. So the next one, and it's a pretty lengthy example as you can see. Okay. So the next one that we're going to do is going to be a maximum distortion energy criteria. Okay. And another words is also known as vormesis or vormesis. Okay. In other words, it's also known as vormesis. So now what is this energy? Okay, so the distortion energy, I'll tell you the units first. Okay, so the distortion energy per unit volume. So it's per unit volume that we are looking at. Okay, per unit volume. Right, it's under plane stress condition. And I'll explain to you what do we mean by plane stress condition. Okay, under plane stress condition. Okay, so I'll write for you what do we mean by plane stress. So in plane stress condition, now the theory is a bit dull, but when applying it, it's not difficult at all. Okay, don't be afraid that okay, what is Eugene meaning by plane stress? I can't remember all this. Okay, don't worry. When we do an example on it, okay, it is not that bad. Okay, so in plane stress condition, one of the normal stress direction is equal to 0. Okay, must be equal to 0. So if I have a 3D element, so I'm going to draw a 3D element now. So this is X, Y, and this is our Z. So I'm going to sketch a 3D element. So these are our direction. So this is our stress X, stress Y, and stress Z. Okay, and you realize that I did not draw any shear, means there's no shear at all. Okay, so in plane stress condition, okay, in plane stress condition, hold on. there are three situations. Okay, is where stress X and stress Y are not equal to 0, but stress Z is equal to 0. Okay, so that is one condition. Or stress X and stress Z are not equal to 0, but stress Y is equal to 0. That is also a plane stress condition. Okay, then we have another condition where stress Y and stress Z are not equal to 0. For this case, stress X is equal to 0. So we have condition number 1, condition number 2, condition number 3. So when von Mises developed his criteria, right, it will work with either condition number 1 or condition number 2 or condition number 3. Okay. So now, based on distortion energy, right? So I'm going to introduce you to his formula now.